Hello, this is a pre-recorded video on the second experiment for Physics 71.1. The second experiment is on measuring devices. So for this experiment, we have four learning outcomes. So first, we want to determine the least count and uncertainty of different measuring devices. So the least count will be a concept that we will be discussing during this experiment. So secondly, we want to measure the dimensions of an object using different measuring devices like rulers, Vernier calipers, and micrometer calipers. And number three, we want to measure the mass of an object using a weighing scale. And lastly, we want to calculate the density of different materials using the measurements that we have obtained using these various devices. So let's have a short introduction. Measuring devices are tools used to quantify observables. Examples of measuring devices vary vastly in the field of physics, from as simple as rulers and weighing scales to as complex as particle accelerators and scanning electron microscopes. But no matter how simple or complex a measuring device is, I want to emphasize this, it will always have a limitation that must be appropriately reported by its uncertainty. So now let's move on to least count. So what is a least count? The least count of a measuring device is the smallest quantity that it can measure. It is usually the smallest graduation or mark in a measuring device. So for an analog device, like rulers, the device's uncertainty is given as half of the least count. And for digital devices, such as the weighing scale to be used in this experiment, the uncertainty is equal to the least count unless specified otherwise. Again, as a reminder and call back to the first experiment, number of significant figures of the uncertainty must always be only one. All right. So just as a clarification here, just in case you would not be familiar with these terms, analog and digital. I will be typing on my Microsoft Word here on the left. So basically, an analog device is one where you read the measurement by basing off the available scales. So just like with the ruler with markings that denote your measurements, you will be reading and interpreting the results by yourself. Now, on the other hand, you have here your digital device. So everything is computerized. Results will automatically show up on the screen. So you don't really need to do any thinking or comparing if your measurement is correct. I mean, what you would do here is just read it and that would be your measurement. So next, let's talk about the scales of measuring devices. So for this experiment, we will be using four devices, which are your ruler, your Vernier caliper, the micrometer caliper, and your digital weighing scale. So for reference, I will be opening your data set. So this is the data set that you will be using when you do this experiment. So your tools here would be your ruler. Of course, all of you would probably know what a ruler looks like. Just basically a stick that's usually 1 foot long with measurements in both imperial units like inches and metric units like centimeters. We also have here your Vernier caliper. Now, this may not be as familiar to some of you, but this one is a more precise measuring device as compared to your ruler. And of course, you also have your micrometer caliper, which also has a better precision compared to your ruler. And lastly, we have here your digital weighing scale. So in a digital weighing scale, you just put your object in front of this silver plate here, and its mass will be measured automatically and shown on this dark blue screen here. All right. So let's go back to our manual. So going back to the scale of measuring devices, each device has its own graduations or scales, which can be summarized into three. So your final reading, which will be the serving as your central value, is the sum of all the readings from each scale present in the measuring device used. So for example, I have here a final reading. It will be equal to my three scales. So these are main scale, fractional scale, and estimated scale. Main scale plus fractional scale plus estimated scale. So what are each of these scales? So basically, you have here your main scale. This is your least precise scale and is usually improved upon by the other scales. So for each device, the main scale, fractional scale, and estimated scale may change. But in general, this is how they are defined. So your fractional scale is an additional measurement that is a fraction of the main scale. So this one is important. Only certain devices have this. And lastly, you have here your estimated scale. This is an additional degree of measurement. And just like the name implies, it's not just up to your device, but rather up to your personal biases when you estimate a certain degree of precision for your measurement. So it's based on your judgment. And as you recall from the first experiment, uncertainty, the judgment of the experimenter is one of your causes for uncertainty. Okay. So now let's go to our devices. So let us first discuss the ruler. So all of you have most likely seen a ruler before. So the ruler used to be used in this experiment will have two different least counts depending on the length of the object being measured. So this part, let's just ignore this part because it is confusing and it's not relevant actually to the experiment. Let's just skip directly for this. Let's just skip directly to this part here. So for objects longer than 10 centimeters, the least count is 0.1 centimeters. So that is an analog device. Your ruler is analog, so the uncertainty is just half of the applicable least count. So in this case, for a ruler, your least count would be 0.05 cm or 0.5 millimeters. So you can actually base this least count based on these lines here. So in a standard ruler, each large number here denotes 1 centimeter. And these centimeters are further subdivided into 10 lines, which denote 1 millimeter each. So you have here your shorter lines here. However, for the ruler used in this experiment, medyo mas special siya, ano? It has lines that denote half millimeters or yung least count nga. So this ruler is more precise than others, but note that not all rulers will have this kind of design. So this figure here shows the measurement of the radius of a 5 peso coin. So in this figure, the main scale reading is 2.6 centimeters. So how can we tell? So let's zoom in a little bit. So here we have 2.6 centimeters now. How did they do this? So let's measure this. Let's draw a line. So here, the 5 peso coin is situated near the 0 point of the ruler. And when you measure it, it coincides with this line here. So this line here would coincide to 2.6 centimeters. Okay. So let me just type here. So this would be 2.6 centimeters pala, sorry. So now that we have a main scale reading, so the fractional scale here can be any other number less than the least count to be decided by the user. So medyo ano to, no? Tansyahan na siya. So as an example, since the least count is 0.05 centimeters, the fractional scale was set to 0.03 centimeters. So note that this fractional scale here is entirely up to a guess. So where did this guess come from? So dito, if you see the measurement here, zoom in yung measurement ng 2.6 centimeters na piso, 5 piso. And again, hindi sakto yung measurement ng 5 piso doon sa line. So it's not really a exact measurement. So instead of using uncertainties na may plus minus, yung ginawa dito for the measurement is sinet to 0.03 na estimate yung least count. Ay, yung fractional scale reading pala, sorry. Yung fractional scale reading. So this adds a degree of precision to the measurement. So yung main scale plus fractional scale reading. So final reading would be main scale plus fractional scale. So yung ginawa niya ay final reading is equal to 2.6 centimeters plus 0.03 centimeters or 2.63 centimeters. Now, the uncertainty here is half the least count. So again, half the least count is 0.05. So the uncertainty should be 0.025 cm. However, both round-off rules and the one significant figure rule for uncertainties will apply. Therefore, kailangan i-round off itong 0.025 into 0.02 cm. So again, 0.025 was rounded off to 0.02 cm using round-off rules found in the supplementary material of the first experiment. So using these uncertainty and central values, we have a reading of measurement 2.63 centimeters plus or minus 0.02 centimeters. Okay, so that's it for your ruler. Now let's move on to our Vernier caliper. So a Vernier caliper can measure lengths in 3 different ways: using its clamping mouth for inner diameter, using another clamping mouth for an outer diameter, and by using its depth probe to measure depth. So the depth probe is located at the other end of the caliper opposite of the clamping mouths. Only the clamping mouth for outer diameter will be used in this experiment. So before we proceed with the reading scales, measurement scales, let's have a short demonstration on how we use Vernier calipers. So I have here a set of videos. So let me show you. So this one is a standard Vernier caliper. So here we have, if I play this video here. So this circular nudge can be rotated to make the caliper quote unquote open up. So let's see here. So using the clamp, this person here in the video is measuring this clock from a watch. So you clamp it again and see that there are corresponding scales on the Vernier caliper itself. So this is where the readings will come from. So using this clamp, you can measure your outer diameter. So this is the part that we will be using for measurements in the experiment. Although I do want to show you guys other applications. So this is how you will be measuring inner diameters, for example. So I'm going to mute this video. So let's just let it play for a while. So this person measured this cup, the outer diameter of the cup. here. Here I have an example for measuring the inner diameter. So this set of clamps here on top of the vernier caliper can measure the inside diameter of objects. So as a demonstration, this person will be measuring the inner diameter of a beaker. So let's see how he does that. So first, he uses these clamps, upper set of clamps and jaws. And of course, there will be a corresponding reading scale for this inner diameter. Now, lastly, we have here for your depth probe. So the depth probe is basically a stick that protrudes outward from your vernier caliper when you move your measurement device. So, for example, this person will be moving the vernier caliper around, and as a result, this little rod will protrude out of the vernier caliper, and you can use this to measure the depths of your objects. So when the person rolls this apparatus, the depth rod will protrude out, and it will have a corresponding measurement using the same scale used for the clamping jaws. All right. So with that, let us go back to our course material. So let's now discuss the scale readings for the vernier caliper. So the main scale reading is measured based on the 0 mark of the vernier scale. So now let's move to this picture here, figure 2. So our vernier caliper that measures the thickness of your 5 peso coin. So the main scale reading will have a 0 mark. So ito yon, to may malaking 0. So the fractional scale, on the other hand, is obtained based on which mark on the vernier scale matched with the mark of a main scale. So there is no estimated scale here. So the final reading would only be main scale plus fractional scale in the case of a vernier caliper. So instead, the estimated scale is replaced by the act of selecting which marks match, which will now depend on the judgment of the user. So here, let us focus on this figure here. So in figure 2, the 0 mark indicates that the main scale reading is 1 millimeter. So how did they do that? So basically, let us zoom in here. So the bottom scale here denotes the reading for your main scale. I mean this one pala. This large one. This large one is for your main scale. So just to clarify, I will be inserting a line here. So this line here will measure your main scale. All right. So let me just type here. Main scale. So in this measurement, the 0 mark of the smaller scale here will denote the main scale measurement. Where does it coincide with the big scale here? So since the line of 0 here will coincide just before the 2 millimeter mark on the main scale, so yung 0 na ito nakatapat just before the 2 millimeter mark, we say that the main scale reading is 1 millimeter. Okay? Hindi siya umabot sa 2nd millimeter mark based on this picture. So the main scale reading should still be 1 millimeter. Just like the manual tells us. So now, next, the vernier scale has 50 marks. So what are these marks? So let us delete this first. So this vernier scale, itong mas maliit, ito na yung vernier scale natin. So kung mapapansin natin, this goes from 0, 1, 2, all the way up to 10. And each set of lines between any two numbers totals 5. So, halimbawa dito, from 0, 1, 2, 3, 4, 5. 5 lines hanggang sa makapunta sa 1. And now, since 5 lines ito per number and there are 10 numbers, so this is where your 50 marks will come from. So, next, for the fractional scale reading, based na dito sa scale na ito. So, it can be seen that the 45th to 50th marks almost match the main scale marks. So, here, we want to look where the fractional scale lines match the main scale lines. For example, so dito sa Vernier scale natin, di magkakatapat yung lines. So, di ba, may breaks dito. So, what happens here is that this trend will continue for a while until maybe yun nga, the 45th to 50th marks. Let's look at this 40th to 50 marks. So, ito yung 40, 45, 50. So, nag-coincide yung lines na ito with each other. So, dito ka magbe-base ng measurement mo. So, how do you read these measurements? So, the 45th to 50th marks, so 9 to 10. So dito, itong set na ito almost match the main scale marks. 46 to 51 dito naman sa main scale. So example lang daw, they choose the 47th mark on the Vernier scale. So step 1 yung main scale reading. Step 2 is choosing marks on the Vernier scale that coincide with the main scale. So step 3 mo naman, counting these marks. So bawa, so 47th mark nga daw. So yung each mark dito, so basically, clarify ko lang pala para mas madaling intindihan. The 47th line was chosen. So, for example, dito, ano yung 47 na ito? This is the 47th line on this Vernier scale. So, again, this is 5, 10, 15, 20, 25, 30, 35, 40, 45. So, pinili niya yung 46 and 47. So, this line here, so magkatapat nga daw halos. O magkatapat nga. Kita ko rin, magkatapat sila. So dito, itong line na to, no, pinili niya yung 47th mark, meron din dito nakalagay sa Vernier scale na 0.02 millimeters. So this 0.02 millimeters na reading shows you the corresponding measurement for one line. So, dahil dyan, step 4, determine what measurement equivalent one line in the Vernier scale corresponds to. The step 5, multiply the number of marks you chose in step 3 with the equivalent measurement of one line in step 4. So this will be 47 times 0.02 millimeters, 0.094 millimeters. So ito na yun. So ito na yung fractional scale reading natin. So fractional scale, so 0.94 millimeters. And yung ating final reading should be 1 millimeter. So yan yung main scale plus 0.94 millimeter equal to 1.94 millimeters. Ngayon, we also have a uncertainty. So again, dito sa Vernier Caliper, itong 0.02 millimeters na mark ito sa Vernier scale, this will be your least count. So yung least count mo dito would be halved to get the uncertainty. That's why meron tayong nakuha na 0.01. So measurement would be 1.94 plus minus 0.01 millimeters. So again, just to note this, the least count of the Vernier caliper. So again, yung smallest na pwede mong ma-measure is equal to the equivalent measurement of one line on the Vernier scale, which is 0.02 millimeters in our case. All right. So, next naman, let us discuss our micrometer caliper. So, micrometer caliper has only one clamping mouth, unlike your Vernier caliper, which has two. And the object must be placed in between the mouth and must be tightened by rotating the thimble. So, di naman kayo maghahawak, pero it's nice to know pa din na when handling these kinds of equipment, you have to be careful and not tighten it too much kasi pwedeng masira ang either yung micrometer caliper or yung object. So before we proceed on how we determine the readings of the measurements, let us first determine or see rather how this micrometer caliper is used. So in this video that I am showing now, I am using or I am showing a micrometer caliper. So let's play the video a bit. Oops, sorry, I didn't pause. So this micrometer caliper will be used to measure the screw. So the micrometer caliper thimble is rotated para maipit yung screw, and if papansin niyo, may corresponding scale reading dito sa part na ito. Yung just before the clamp. Again, nilalak yung measurements in place para hindi siya magulo. Pwede tanggalin yung object and the measurement will be retained. So that's basically it, no? That's how you will be measuring things using micrometer calipers. So now let's move on to the readings of these scales. So nandito, based yung numbers, dalawang set of numbers ang babasahin natin. So let's go to that. Pause. Okay, so the main scale reading is obtained by counting the marks not covered by the thimble. Integer marks are above the solid line and half value marks are under it. So, in figure 3, let's go to, where's figure 3? Okay, here we go. So this is figure 3, measuring the, well, diameter, thickness pala, thickness pa rin ito, of a 5 peso coin. So, ang main scale reading, again, integer marks are above the solid line. Half value marks are under it. So how do we determine this? Let us zoom in to this measurement. So you have here your solid line. So yung solid line natin dito ay itong part na to. Let me draw a line over the solid line. So this one is your solid line. So integer marks are above the solid line. So if I were to write, so this will be my 0 point and this would be 1. So i-extend lang natin. I want to type 0 and 1. So if papansinin ninyo, hindi magkatapat exactly yung lines ng taas at baba. This is because half integers naman ang binibilang nung nasa baba ng solid line. So for example, I want to measure this line. So this line is in between. So the line under is in between the integer marks. So nasa ilalim lang siya just for ease of use. So for example, this would coincide to a measure of 0.5. So these are half integers. So following that same logic, so this is 0, this is 0.5, this is 1. Of course, the next measurement would then have to be 1.5. So this is how you make your measurements. All right. Well, let us now zoom out again. So again, ang sinabi niya, the main scale reading of the peso coin is 1.5 millimeters and the half value mark is already visible. Now, let's move on to the fractional scale for the micrometer caliper. So, the fractional scale is obtained from the scale on the thimble itself with the solid line as the basis. So, let's move to this thimble. Now, I will be deleting this first to make things simpler. So, again, this is your solid line. So, on your thimble, you have here scales that are on the other axis. So, opposite axis. Kumbaga, if this was the x-axis, naka-y-axis itong ano mo, ibang scales mo. Kasi iniikot mo yan eh. So, habang gumagalaw siya. Anyway, that would be a slightly confusing explanation, but the point is, ibang scale na ito, itong nasa thimble mismo. So, let's look at the thimble. So, the solid line is your basis, and the way to do it is to count the number of lines again. So, the numbers here do not actually denote lengths, but rather, yung number of lines na yung binibilang nila. Although may equivalent measurement din sila naman. So in this case, ang reference natin is this is 35th line. So in between the solid line are the 36th and 37th lines. So let's note that 36th and 37th lines are nearest to the solid line. So let's see how this is read. So ayun, with the solid line as the basis. In the figure, yung 36th line na. Yung 36th line na yung pinili niya. So malapit na din. Hindi eksakto pero malapit. Pinili niya yung 36th line. So let us write step 1. So main scale reading, integer measurements are top of the solid line. Half integer measurements are bottom. Step 2, determine the number of lines. The number of the line that coincides the solid line. Number of lines, the number of the line on the thimble that coincides with the solid line. So in this case, it is the 36th line daw, sabi ng ating manual. So step 3, note the equivalent measurement of each line on the thimble. So in this case, each mark on the thimble is equivalent to 0.01 millimeters, which is the least count of your micrometer caliper. So 0.01 millimeters daw. Step 4, multiply the number of the line coinciding with the main scale solid line and the equivalent measurement of one line. Okay, so we have here 36 times 0.01 millimeters is equal to 0.36 millimeters. Next, we have here your estimated scale naman. So again, yung estimated scale, this coincides, this factors the fact na hindi sakto yung ating 36th line sa solid line. Actually, in between ng solid line, yung 36 and 37, ano? So, going back, so the estimated scale based on how far the solid line exceeds the thimble mark must be lower than 0.01 millimeters. So, bakit? Kasi one line on the thimble is already 0.01 millimeters. So, ibig sabihin yan, pag mayroon kang in between, that's less than 0.01. So dito, estimated scale, as the name implies, magtatansya na lang tayo. And yung tansya niya ay sinet niya 2.004 millimeters as an example. So to summarize, step 5 muna. So estimated scale, note that the estimate must be less than the least count. So to summarize, you have here your main scale, 1.5 millimeters. You have your fractional scale, which is 0.36 millimeters. And estimated scale is 0.004 millimeters. So all in all, your final reading would be the sum of all these measurements. 6 millimeters plus 0.004. So this would be final reading 1.864 millimeters. So note dito na again, we do have an uncertainty to factor in. So again, the least count for micrometer caliper was or is 0.01 millimeters. Uncertainty is half the least count. So it is 0.005 millimeters. So ang measurement natin dapat would be 1.864 millimeters plus or minus 0.005 millimeters. Okay. So lastly, we now discuss our weighing scale. Digital na ang device na ito. So it's not like the previous 3 devices that we have discussed so far. So now let's discuss the digital weighing scale. So the digital weighing scale used in this experiment gives the mass of the object in grams. So to use the digital weighing scale, it must be first calibrated properly. Oh, by the way, the least count is already given here. So ang least count, binibigay na ng measuring device manual agad kapag digital. So again, dapat makalibrate ang digital weighing scale kasi in some cases, pwedeng mag-cause yan ng systematic error if not properly calibrated. Again, if you recall, systematic errors are consistent errors in measurement resulting from faulty assumptions in the equipment. So this includes not calibrating. So ayun, kinakalibrate ang weighing scales. Although for this experiment, kasi remote learning, you won't need to do that. Okay? So let's skip this example kasi di naman siya kailangan. Anyway, dun sa weighing scale mismo naman, ay babasahin lang ang reading ng mass na ipoproduce niya kapag may pinatong tayo sa kanya. Okay? So yung pinaka-point ng pag-calculate ng lahat ng ito is to calculate the density of an object. So density is mass per unit volume. So in formula terms, you have your density rho. It's your mass divided by your volume. So your density is a constant relating to whatever material your object is made of. So in this experiment, ito na yung pinaka-goal natin. We would be measuring the weight and dimensions of the samples using the given devices, and the data would be used to compute for the sample densities. So, yung materials natin dito, we already have your measuring devices, ruler, Vernier caliper, micrometer caliper, digital weighing scale, and metal samples. So basically, nandito naman yung instructions. So gagamitin natin itong data set. So yung data set, nandito na actually yung measurements. So you are going to measure a rectangular metal sample and a cylindrical metal sample. So all of the measurements are already done for you in this case. So you have here your measurements by your micrometer caliper. So paano natin babasahin ito based on the lessons earlier? Meron tayo Vernier caliper na measurement din. So paano babasahin to? And of course, you have your ruler measurements. And again, sa weighing scale, nandito na yung ano natin, yung measurement natin. The same din sa cylindrical metal sample, it is already all measured for you. You just have to read and interpret the measurement correctly. Okay? So, let's move on to your actual data set. So dito, you will be measuring each of the pictures. So naka-organize naman na yung pictures into the different trials, 3 trials per measuring device. And of course, you will have to average your measurement. So you will still be using concepts from the first experiment. So again, recall, how do you determine the uncertainty from multiple measurements? So that's how you'll get the measurement here. Kasi you need the uncertainties for this measurement. So here's your Ovle module for reference. So ayan, pipili kayo ng option ng tama, pero may uncertainties pa rin yan. At dito, i-fill up nyo pa rin manually yung inyong uncertainties. So be careful with that. Tapos dito naman, sa table W2, this will be the same. You will still be doing the same things pero sa cylindrical metal samples. So balik tayo sa ating file. So sa table 3, you have here your volumes and densities of the 2 metal samples. So here you will be doing multiplication. So of course, your volume is your length with height. So how do you calculate that? So you will have to determine yung uncertainty using multiplication and division. Parehas lang naman yan. So note lang, yung mass din ng ating objects, metal samples, may uncertainty din yan. And just browse the manual to determine the uncertainty sa digital devices. I think I may have already mentioned it naman. Anyway, this goes for both the volume and the density. Yung uncertainty using multiplication. Uncertainty propagation. Yes. That's the exact term I was thinking of. All right. So, tatlong tables na yan. Field tables W1 to W3 with uncertainties included. Compute the correct uncertainty for measurements with multiple trials. All right. Attach computation. So, we will be requiring you guys to submit your solutions kasama rin sa points yan nung experiment. And lastly, for the questions, again, as usual, answer in no more than 2 sentences. So these are again conceptual questions lang naman to test your understanding of the material. So question 1, the default uncertainty for an analog device is half its least count, but for a digital device, it is the least count itself. So, ito na pala, yung sinasabi ko kanina for the mass. So, alam niyo na yung uncertainty niya. It's just the least count. So, give a possible reason bakit magkaiba yung least count ng dalawa. So, next question. Tatlo palang questions ito. So, number 2, the density of aluminum is 2.7 times 10 to the 3 kilograms per cubic meter. And for brass, it is 8,400 kilogram per cubic meter. Are your results acceptable based on these values? Why or why not? So, you won't be identifying kung which one is which agad-agad. Makikita nyo na lang yan kapag nakalculate na yung density. Pag may density na kayo, you will be able to identify the material based on the density given. Kasi unique naman ang density. Unique property siya per material. However, maging acceptable ba ang results based on your calculations? So, makita natin, how do you compare this with this theoretical value with the calculated value you have? So, you can use yung deviation from the first experiment to do that. And deviation and percent error, pwede parehas. So based on this, may criteria din sa first experiment kung acceptable ba ang results. So babalikan nyo rin yun. So last question, what are the assumptions you've made in obtaining the densities of the samples? So this relates dun sa question 2, kung acceptable ba or hindi ang nakuha ninyong results for the densities. All right. So that's it for experiment 2. So thank you for watching and good luck.